Alright guys, well, I said I would upload a video detailing a bit more in depth about arc length and about our angular vectors, because they can be a little tricky, especially if you don't have something to watch while somebody's talking about them. So I have a wheel, right? So we can look at how this spins and talk about our relation between our arc length, right? So this is the distance we travel around the edge of our wheel, our radius, right? So our direction pointing out from the center of the wheel, and our angular velocity and our angular acceleration. All right, so to start us off, right, just to recall, our radius, right, it's just from the center out, right? And so our radius vector is pointing from the center out in all directions, right? It's radially out, it's radiating is a nice way to think about it, right? So we can think of it as each one of these spokes is a radial vector pointing out. Right, and that'll come in handy in a bit. But in the meantime, right, arc length, right, all we're dealing with is a change in angle. So if I situate this such that this spoke is pointing down, and this one is perfectly over, right, and then I rotate this one, so now it is perfectly down, and this one's perfectly over. We've changed our angle by some amount. That amount in this case, right, we went from here to here. It's 90 degrees. We don't want degrees though, right? We want radians. And so 90 degrees is pi over 2 radians, right? The conversion factor being 180 degrees equals pi radians. So half a circle is pi. And you can think of it as if you go around a circle one time entirely, right, you've gone 2 pi. And the reason that's important is for our arc length, right? That's this distance along the outer edge of your wheel that you travel, right? So if we go from here to here, how far we've gone? Well, we've gone r, right, our radial distance r times pi over 2 radians, right? And that's how far, that's our arc length, is r times theta, right? So in the case of going around an entire circle, right, that's r times 2 pi, right? Because a whole 360 degrees equals 2 pi radians. So 2 pi r, you might recall, is just the circumference of our circle. And that's how arc length is related to things you may already know. Now, to move on to a bit more complicated stuff, our angular velocity and our linear velocity and how we can relate those. Right? So our linear velocity, right? So if this is spinning and it's rolling and it's translating in some direction, right? How fast is it going? Well, we can relate that to our angular velocity, which is how fast we're spinning it, and our radius. Right? So in that case, our translational velocity, right, is equal to omega, which is our angular velocity, cross r being our radial vector. Right? So it's a cross product, so it gets a little tricky. So a quick review of the cross product is the direction of the cross product that it yields, right? It's your right hand rule. Right? So your first vector is your index finger, which you point in whatever direction it's going. Your second vector is your middle finger, which makes a 90 degree, there we go, 90 degrees with your original vector, so you can point it in different directions. And then your thumb, right, is the direction that your resultant vector goes in. So if we have omega cross r, our thumb is our v vector. Right, and so the trick is, right, we know r is radially out. So the question is, what direction is omega? Well, we can actually think about it by working backwards, right? We know that v is, right, up here, v is going this way. Over here, v is going down. Down here, v is going this way, right? V changes at every point in the circle. And that's part of the reason we use the cross product to define it, right, is because it has to be able to change as we spin around. And again, that's just the plus of the cross product. And so, if we know that v is going this way, if we spin our wheel this way, then what direction crossed with our r, which up here is pointing up, is going to give us over? The answer is out, right? So it's going to be pointed towards you, out of your screen, right? Because we're spinning this way, right? So it's our omega cross our r, which is pointing up if we look at the top of the wheel, right? And our velocity is that way. And indeed, our wheel is spinning this way. And so here at the top, our velocity is going that way. Now, right, again, the reason we define it this way is because we can look at other points on our wheel, right? If we look at this side here, it's currently going down, right? So our omega, right, since it's still spinning this way, omega is still pointing towards you. Our R is out, right, because we're going from here out to this edge, and so our V is down. And we can see that it spins around the entirety of the wheel. And so that always works, right? The plus of this, right, is that our change in angle, our angular velocity, and our angular acceleration are all in the same direction. And that direction is always parallel to the axis about which we spin, right? So if our wheel is spinning along this, it must be either pointing with the top up here out, or this bottom pointing down, right? It has to be parallel to this axis, because our spinning is along these other two directions. And so, right, since it's a vector cross product, we're designing a vector that's perpendicular to some area, such that when we take a cross product, we get the direction we want. Hopefully this makes a bit more sense. If not, you can always email me or swing by my office, right? Whatever works, just let me know. I'd be more than happy to help out. All right, enjoy the rest of your days.